Hello everyone. In this lecture, I shall discuss the linearly independent and linearly dependent set of vectors. Okay. So before coming to the discussion of Li and Ld, let me to introduce myself. Myself, Professor Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai University of Technology, Burla, Odisha. So, before discussing Li and Ld set of vectors, let me to recall the linear combinations. So, what is a linear combinations? You are given V over F be a vector space. Okay, V over F be a vector space. Now, V1, V2, Vn be the vectors in V. Okay, I may write this arrowhead or I may not put the arrowhead, but elements of V are the vectors and the elements of F are the scalars. Okay. Now the linear combination is scalar alpha 1 into V1 plus alpha 2 into V2 plus dot 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 alpha n into Vn. Now whenever this linear combination is called a trivial linear combination, right? Now we equate it to 0. And after equating it to 0, we try to solve it. We just solve it, right? After solving, the situation may arise like this. We may get alpha 1 0, alpha 2 0, and all alpha n are 0, right? Alpha n 0. In short, I write that is alpha I is equal to 0 for all I. If all the scalars involved are 0, then this combination is trivial combination, right? Trivial linear combination, right? Now whenever this linear combination is trivial, then we call it linearly independent. Okay, in short I am writing Li, linearly independent. Now after solving, if I get at least one of the scalars is non-zero, at least one of alpha i's is not equal to 0, right? Then this combination is a non-trivial linear combination. And this non-trivial linear combination lead you to the linearly dependent. Okay, it lead you to linearly dependent. That means we take a linear combination, we equate it to 0. If all the scalars are 0, then we call the system is the set of vectors is Li, or the system involving the vectors is Li. And if at least one of the scalar is non-zero, right, then we call the vectors, set of vectors are LD, linearly dependent, and the set involving all the vectors is a dependent set. Okay, in that way we will interpret. So let me to write the definition and solve some important examples to make your understanding clear. Now come to the definition. A set of vectors v1, v2, vn over a vector space, or the set involving these vectors is said to be linearly independent. I am writing Li if the trivial linear combination results to 0 vector. What does it mean? That is alpha 1 v1 plus alpha 2 v2 plus dot alpha n vn is equal to 0 implies alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. That means all the scalars are zeros. Okay, where alpha 1, alpha 2, alpha n are alpha I belongs to the field, right? Alpha I belongs to the field, right? If all the scalars are 0, so what does it mean? All the scalars are zeros. All the scalars are zeros here, right? Zeros here. Then we say this is a linearly independent set of vectors. Likewise, whenever it is said to be linearly dependent or LD, if non-trivial linear combination results to 0 vector. So what does it mean? That means that is for alpha 1, alpha 2, alpha n in F, alpha 1 v1 plus alpha 2 v2 plus dot alpha n vn is equal to 0 implies at least any one of at least one of alpha i's is not equal to 0, right? Means any one of the scalar minimum is not equal to 0. More than one scalar may not equal to 0, but if we are getting at least one scalar is not equal to 0, then this is called the linearly dependent system. Now let us solve some examples. Suppose you are given a set S is equal to this. Okay, we have to verify whether it is Li or Ld. Here the field is R, right? The field is R here. Solution: let alpha, beta, gamma or ABC be the constant. ABC, the scalars in R. These are scalars. Okay. Let A into, this is my V1, this is my V2, this is my V3. A into 3, 1 minus 4 plus B into 2, 2 minus 3 plus C into 0 minus 4, 1 is equal to 0, right? So we collect the first component, likewise second component. So this implies it is my 3A plus 2B plus my 0C is equal to this 0. I will write it 0, 0, 0. Okay, it is a, means we are talking about a vector RQ over R, right? This is, we are talking about the vector space is here RQ over R. Okay, so now this is equal to 0. Now coming to the second element here, we have A plus 2B minus 4C is equal to 0. And coming to the third element, it is minus 4A minus 3B plus C is equal to 0, right? This is a homogeneous system, right? This system is a homogeneous system. Now you see, I have told you the different approach of solving this. Gauss elimination method is one of the important aspect of solving this. So now if I adopt the Gauss elimination, my intention is to solve for A, B, C. What is the value of A and what is the value of B and what is the value of C? Suppose I adopt here Gauss elimination method. Already I have explained. You should refer to my earlier lecture. Gauss elimination method. If I adopt, right, then what will happen? I consider the augmented matrix. It is my 3, 2, 0, and the coefficient here I am taking. So the coefficient here is 1 here. So 1, 2 minus 4 and minus 4 minus 3, 1, right? I am taking the coefficient. So gently press a line and you have 0, 0 and 0. Okay, you try to bring it to the upper triangular form, right? So we are adopting the Gauss elimination method. We consider the augmented matrix, right? So then I just interchange this and this to bring 1 in this position. Just I interchange here. Any two row we can interchange. So what are the Gauss elimination method is based on your elementary row operations. You can interchange any two row, isn't it? You can interchange any two row and you can replace a row by a constant multiple of that row, and constant should be non-zero constant. And third, you can increase a row by a constant multiple of other row, right? And also at the same time a constant can be multiplied over here, k1, k2 not equal to 0, right? So based on this you should refer to my earlier lecture on Gauss elimination and how you reduce the matrix, right? So now using this we try to bring this position 0 and this position 0. I adopt this row operation, right? Then I just try to make it 1, right? Or at the same time we may directly work out it. So here I just divide minus 4 here, then I use this to bring this 0, right? So now this element is 0. Now what we get? So this is of the form, this is a infinitely many solution here, is not it? We are getting 0 is equal to 0 here. Now we have 2 equations but 3 variables. So here the solution is infinitely many solutions. It leads you to infinite solution, right? That means one variable has to depend upon the other, means if I solve this here, right, it is my, you say b minus 3c is equal to 0, so my b is equal to 3c, right, b is equal to 3c, so here b depend upon c, right. So similarly here a will depend. So you see, actually no need to simplify it. Okay, infinite solution is means one variable has to be independent, right, whatever the value you may choose. So now this row will give you b is equal to 3c, and if you simplify it, it will give a is minus 2c. So here abc is like this, c is independent. If I choose, suppose c is equal to 1, then what is my a is my minus 2, what is my b is my 3, right, you see. So not necessarily abc are 0, right. So that means this system is linearly dependent, right, linearly dependent. So not necessarily means here, not necessarily a is equal to b is equal to c is equal to 0, it's not necessary, right. So once we are getting infinite solution here, means one variable has to depend upon the other. Okay, this is a lengthy approach. I will tell you two more methods for your easy calculation, right. Now if I choose these two, equation 2 and 3, and I apply this simply elimination cross multiplication technique, or you may have what are the other methods you may adopt? You may adopt substitution, or you may adopt cross multiplication, right, or you may adopt elimination, as you read in your higher secondary classes, you may adopt it. Okay, so the cross multiplication is another easy way to solve it. So I adopt here, suppose this is my method A, I adopt. Now alternatively I want to adopt the cross multiplication, it will be a better approach. So coming to the cross multiplication, so coming to another easy way, here a divided by, okay, here a by, while you take a, this into this minus this into this, you should see my earlier lecture. So it is my 2 into 1, 2, it is minus minus plus, minus minus plus minus 12 is equal to, for the second we have minus b divided by, means we are taking this coefficient and we are taking this coefficient, first and third. Here 1 into 1 minus plus minus 16 is equal to here c divided by, for c you have this and this, is not it, it is minus 3 minus plus 8. So this implies here a by minus 10 is equal to here b by 15 is equal to here c by 5, right. So these are all proportional, I can multiply throughout the 5. So my a by minus 2 is my b by 3 is my c by 1. Okay, if I equate it to 1, since these are proportional, what is my a is minus 2, b is my 3, c is my 1, you see here. So now not necessarily 0, so the system is linearly dependent. So if at all we move like this, we should use this, we should prefer this cross multiplication technique to get it, right, to get it. If I want to further extend, if I say suppose this is my k, if I say suppose this is my k, then this is my k. Now I come to my equation 1. Now what happens to my equation 1 now? In equation 1 you have 3a plus 2b is equal to 0. So you substitute that 3a plus 2b is equal to 0. 3a plus 2b is equal to 0. You see here what will happen. So it is minus 3 into 2k, okay, plus 2 into here 3k, right, is by default here 0. So what is the k? So k is anything, k is arbitrary here, is not it, k is arbitrary here. So if I choose k is equal to here 1, if I choose, then I am getting here a is equal to minus 2, b is equal to 3 and c is equal to k. That means all a, b, c are not necessarily 0, so therefore the system is linearly dependent. Now I am telling you one easy way, right, one easy way I will tell you, and easy way, easy approach. So you think about this working rule here. So what is the working rule for this here, for shortcut? The working rule, right, means you write a matrix. Step 1, consider a matrix by taking the given vectors as row, vector. Consider a matrix A. Let the name of the matrix be my A, say. Okay. Then what I do in the second step? In second step, what I do is find the rank of A. Find the rank of A. Right. And third step, if rank of A is equal to number of row vector, right, then it is Li. Then Li, right. If it is not equal to number of row, then it is your LD. So let us adopt this technique here, right. Let us adopt this technique here. So by adopting this technique, so coming to the alternative solution as we discussed earlier, right. So here what is the matrix? Let my A is equal to 2 minus 1 1 3 4 18 minus 1 2 minus 4, right. So I consider this matrix here. This is a 3 cross 3 matrix. So what should be its rank? The rank has to be at most 3 and minimum 1. It is a non-zero matrix here. So now I find just the determinant of A. What is my determinant of A? It is my 2 into minus 16 minus 26 plus 1 into here minus 12 plus 8 plus 1 into 6 plus 4. Okay. So if I simplify it, it is 2 into minus 32 plus of minus 6 plus of my 10 here. So it is my 64 minus 64 minus 6 plus here 10, okay, which is not equal to 0, right. So therefore my rank is equal to 3, which is equal to my number of row vector. Just a minute. Actually this is a different example. So this set of vectors are Li or LD. So I just take the vectors as the row vectors. Okay, I take the row. Now the rank has to be within this. Now I find the determinant is not equal to 0. So therefore the rank is equal to 3 is my number of row. So therefore the system is, so the set of vectors is here linearly independent, because I am getting number of row is my rank of the matrix. But if I adopt this same technique over here, right, if I adopt this same technique over here, then what is my here A? Here A will be here 3 1 minus 4 2 2 minus 3 3 1 minus 4 3 1 minus 4 here 2 2 minus 3 0 minus 1 4 0 minus 4 and here 1 0 minus 4 and here 1. Okay, and if I find my determinant of A, if we work out it is 3 into here 3 into it is 2 minus plus minus 12. Okay, and similarly my minus 1 into this, similarly my 4 into this. If you find it is at 0. So therefore your rank is not equal to 3, because it is a third order matrix. The rank is not equal to 3, but number of row is equal to equal to 3. So therefore the set of vectors here is LD. Okay, so by this technique we got it LD, and by this technique also we get it here LD, right. So now it is the easy approach to get it. Okay, it is the easy approach to get it. So now let us solve some more examples. Also I will tell you some important remarks in this regards. I will now explain you some important property, right. So if a set containing a zero vector, a set containing a zero vector is always linearly dependent. That means if suppose I have 2 3 4 0 0 0 and 5 4 6 say 5 4 6 say here, so then definitely this is a LD system, right? Now the second property is if one vector is a multiple of other, then also this is linearly dependent. If one vector is a scalar multiple of other, then the set is LD. Okay, suppose I write 2 3 4 4 6 and 8 5 7 3. So what we see here, you see, and this is a multiple of this, is not it? So now this system has to be here linearly dependent. Next, any subset of Li set is Li. Fourth, any superset of LD set is LD. You see, suppose if I going to add one extra element here, then still it is LD, is not it? So any superset of LD set is LD. Similarly, any subset of Li set is Li, right? Now coming to one important set question, what about the phi? Phi means here nothing, right? Phi means here nothing, and it has to always Li, because we are not getting anything to be a multiple of anything, right? Because we are not getting anything to be a multiple of anything, that's why it is linearly independent. So phi set is always linearly independent set. If at all I think of the linear combination of phi, okay, then it has to be like this, right? It has to be like this. Now coming to what about a singleton set? Suppose you are given a singleton set, okay. If the singleton set is 0 here, and if it is not equal to 0 here, right, and if it is A itself and A is not equal to here 0 here, right, then it is always linearly independent here, it has to be always linearly dependent, okay. It has to be always linearly independent. The reason is you see here, because if you take k into this 0 vector, my 0 is 0, so k is not necessarily 0, right? The scalar is not necessarily 0, so this is my linearly dependent here. But if I am taking alpha into A is equal to 0, so alpha is my 0 here. Since A is not equal to 0, I am getting the scalar as 0 here, so this is Li, is not it? Okay, this is Li here. So now so a singleton set, if it is non-zero, then Li. If it is 0, right, if it is 0, then it is LD, right? So you should remember this for short questions here. And the phi is always a linearly independent, because there is nothing to be a multiple of anything, right? But however, if we take the linear combination of the phi, then it is a 0 element here, okay. Let me to solve some additional examples. Are the set of vectors, suppose your question number 1 1 0 0 0 1 1 0 and my suppose 1 1 1, I am giving these 3 vectors, okay. So these are Li or LD. If at all I am adopting, if I let my alpha beta gamma be scalars, okay, because here we are taking 3 tuples here, means it is set of vectors in RQ and this scalar is my R here, right? So if you while you learn vector space, then this knowledge will helpful to you, okay. But if we don't think of the vector space, ordinarily vectors are given and we are just testing, then let alpha beta gamma be scalars here. So then what will happen? Alpha into my 1 0 0 plus my beta into my 1 1 0 plus my gamma into 1 1 1 is my 0 0 0, okay. So let me to simplify it. So taking the first component here, alpha plus beta plus gamma is equal to 0. Taking the second component here, taking the second component here beta plus gamma is equal to 0, beta plus gamma is equal to 0, and taking the third component here 0, 0 and gamma here, gamma is equal to 0. So gamma 0, if I substitute it here, beta 0, if I substitute this to here, then alpha 0. So what I am getting? Alpha is equal to beta is equal to gamma is equal to 0. All these scalars are 0. So therefore the system with the given vectors is linearly independent. Now if I adopt the alternative technique here, I consider a matrix. Let A is my taking the row 1 0 0 and 1 1 0 and my 1 1 1. You see here, this is a triangular matrix, lower triangular matrix here. Okay, what is my determinant of A? Determinant of A is simply the product of the diagonal element is equal to 1, which is not equal to 0. What is the order of this matrix? Is 3. So determinant is 1, which is not equal to 0. So therefore my rank is equal to 3 here, right? Rank is equal to my 3 here. And how many row? Number of row is 3. Number of row. Therefore the system is linearly independent, is not it? The system is linearly independent. Okay. In second question, suppose you are given the vectors is 1 9 9 8 and 2 0 0 3 and suppose 2 0 0 8. So these are the vectors given to you here. Okay. So we have to find the rank again. So I consider the matrix. Here, right? I consider the matrix here. So my matrix is 1 9 9 8 2 0 0 3 and 2 0 0 8. Okay. So if I think of the rank, this is the order 3 cross 4. So rank is minimum 1 and maximum 4 here. Maximum here 3. Maximum is here 3 here. But we have to check for different set of matrices, square matrices. Okay. So but I adopt the Gauss elimination technique to find the rank here, right? So I just use it to bring these elements 0 here. Here R2 is replaced by R2 minus 2 R1, and here R3 is replaced by here simply R3 minus R2. Okay. So you just find it out. So you see, if I simplify it, it is my R2 minus 2 R1 here, and it is simply this minus this. Then it is in the simplified form. So the number of non-zero row is 3. So rank is equal to my 3. And how many row vector? Number of row vector. So the system is linearly independent. Therefore the system is linearly independent. Suppose you think of one more example. Question number 3 say. Question number 3. You are given a set of vectors 1 minus 1 1. Then here 1 1 minus 1. Then here minus 1 1 and 1. Then here 0 1 0 0 1 0 you are given. Okay. So test LI or LD. So if you take the matrix, let my A is equal to, I take the vectors as row 1 minus 1 1 1 1 and minus 1 minus 1 1 and 1 0 1 and 0, right? So what is the rank of this matrix? So the order of the matrix is here 4 cross 3. So the rank cannot exceed here, right? The rank you see here, rank has to less than equal to 3. So since rank of A is less than equal to 3, but number of row is equal to here 4. So therefore, right, therefore the system has to be here linearly dependent. Okay, the system has to be here linearly dependent, right? Suppose you are given another question. Suppose question number 4, you are given 1 2 3 and you are given 0 0 0, you are given 5 5 1. And what can you say about this system? What can you say about this system here? Since you are getting one row is 0, this has to be definitely linearly dependent here. Okay. Suppose you are given one more example. So now if you take this determinant of A, let my A is my 1 by 4 0 minus 1 by 4 0 half minus half 1 by 3 minus 1 by 3 and 0. If I take the determinant of A, here determinant of A will be 0 here, right? Therefore the rank is not equal to 3 here, but number of row is 3. Number of row is equal to 3. rho is equal to 3, right? So therefore this system has to be linearly dependent. Now let me to solve few more questions. Coming to one more question. Suppose find the parameter alpha such that the following systems is LD. Following vectors are LD. Okay. So it is already given the vector is LD. Means the rank is not equal to 3 then. Right. If I am writing my let A is equal to my 1 1 alpha, then 1 0 alpha 0 alpha 0, right? And since this is LD, let A is equal to this. Since the given system is LD, linearly dependent, so therefore determinant of A is 1 1 alpha 1 0 alpha 0 alpha 0 is equal to 0 here. Okay, if we evaluate this determinant by third row, I am evaluating, so my minus alpha into, okay, I am taking 1 alpha, right? So what will happen here? This is equal to 0, right? So this is my this alpha is here arbitrary here. If you put any alpha, so alpha is arbitrary here because you see here minus alpha into 0 minus 0 is equal to 0. So by default alpha is anything, right? Alpha is arbitrary here. So find the parameter alpha. So the value of alpha is arbitrary. Okay. Now come to one more question. Suppose one more question. It is asked that so that these three vectors are dependent and find their dependency. Okay. So solution, let my A is equal to, I am taking 1 1 1 1 0 1 0 1 0. Okay. So what about my determinant of A? My determinant of A here is, I am expanding by the last row. So by minus 1 into, right, it is this and this omitted. This is my 1 1 1 1. Okay. So this is my 0. Minus 1 into 0 minus 0 is 0, right? So therefore it is dependent. Rank is not equal to 3. So that means my rank is not equal to 3, but number of row vector is equal to my 3. So therefore this is my dependent. Now what is the dependency you see here? If I add this and this, right? If I add this and this means if I add, what is the dependency here? If I add here V2 plus V3, right? If I add this two row, this plus this plus this, now it is my V1. So this is the dependency. Okay, this is the dependency. So this is what the rank of the matrix. Now I have discussed the different aspects of this rank. Now if it is a short question is given, then our working rule by the determinant method is fine. If it is a long question is given, then you have to think of the definition method, right? You have to think of the definition method as I have told you, and in definition method it is better you should adopt the elimination technique to get the values of the scalars easily, right? However, if it is a short question, then you adopt the determinant method. Also the remarks what I have told you, this will be helpful for easy access to the problem being asked in the GATE examinations and in other competitive examinations. So now my request to you, if you feel this lecture is interesting and helpful to you, just subscribe to this channel, which boosts my motivation to prepare similar lectures for your benefits. So thank you all. Have a nice day.